Welcome to the Explainer. I am absolutely thrilled to have you here today because we are taking a fascinating, fully under the hood journey into the real mechanics of machine learning. If you've ever wondered how a massive neural network actually learns to look at a grid of pixels and say, yep, for sure that's a cat, you are in the exact right place. We're going to cut past the hype and dig right into the actual engine of artificial intelligence. Okay, let's dive into this roadmap. We'll look at how networks learn, the math of backpropagation, choosing activation functions, fixing unstable gradients, and finally optimizing our training speed. If some of these mathematical concepts sound heavy, do not worry, we are going to break them down step by step. Section 1. How neural networks learn. The core loop. We really got to keep our eyes on the ultimate prize here. The goal is to take a piece of data, like an image of a cat that's been flattened into a long vector of numbers, pass it through layers of artificial neurons, and get an accurate prediction out the other side. To get that prediction, we follow a four-step loop. First, we forward propagate the data through the network to get a guess. Second, we compute the cost, also known as the loss function, which is basically asking, okay, how wrong was that guess compared to reality? Third, we backpropagate that error backward through the network. And finally, update the weights so the next guess is just a little bit better. So while forward propagation gives us our answer, backpropagation is the magical step where the network actually learns to detect that cat correctly. Section 2. The math of backpropagation. Time to decode those derivatives. Look, the raw calculus formulas for this can look completely intimidating at first glance, but just treat it like a puzzle. We are just tracing an error backward one piece at a time. So the crucial point here is the chain rule. When we want to know how much a single weight in the very first layer of our network messed up the final output, doing direct math is a total nightmare. There are just way too many connections. So instead, we use the chain rule to decompose that massive derivative into a sequence of smaller, bite-sized derivatives that multiply together. It allows us to pass the error backward, step by step, from the cost function to the earliest layers without getting stuck. But here is a brilliant shortcut that actual practitioners use. In higher dimensions, doing raw scalar calculus by hand gets unbelievably messy. Shape analysis becomes your best friend. If you know you're taking the derivative of a scalar with respect to a higher dimensional matrix, your resulting answer literally has to match the shape of that matrix. If you end up trying to multiply a 1x2 matrix by another 1x2 matrix, well, you know you've done something wrong. You just transpose one of them into a 2x1 matrix to make the shapes fit perfectly. It's an incredibly practical trick to ensure your math stays on track. Now, here's a quick question for you. When you write out the math for backprop, you'll notice that terms from the forward pass just keep showing up in your backward math, things like the linear inputs or the layer activations. So why do we intentionally cache or save these specific values in memory during that initial forward pass? The answer is purely for computational efficiency. Think about it. If we didn't cache those values, every single time the backward pass needed a variable, the network would have to screech to a halt, go all the way back to the beginning, and rerun the entire forward propagation just to find it. Caching prevents this massive waste of time and processing power. Moving right along to Section 3, Activation Functions, adding nonlinearity. To see how this builds into a real-world architecture, we gotta look at the functions sitting inside our neurons. If you build a deep network without activation functions, meaning you just use identity functions where the output equals the input, it literally doesn't matter if your network is 10 layers deep. It algebraically collapses into nothing more than simple linear regression. It could never ever detect something as nuanced as the curve of a cat's ear. But by throwing in nonlinear activation functions, boom, the network suddenly gains the flexibility to mimic highly complex, nonlinear patterns in your data. Now, what's really interesting about this slide is how these functions actually behave. Take the sigmoid function at the top. It's awesome for outputting probabilities because it squashes numbers between 0 and 1. But there's a huge catch. If the input is really high or really low, the curve completely flattens out, the slope hits 0, your gradient vanishes, and the network just stops learning cold. Tan has that exact same problem. But look at the bottom row, ReLU. For positive numbers, ReLU is just a straight line with a slope of exactly 1. The signal zooms right through without vanishing. That right there is exactly why ReLU is the standard choice for the hidden layers of almost all modern neural networks. Section 4. Fixing gradients, vanishing and exploding. These gradients are the absolute villains of deep learning. They show up when our beautiful mathematical theory meets the harsh reality of a deep network. Picture a 10-layer network. If your initial weights are even slightly above 1, say 1.5, that number multiplies by itself 10 times across the layers. The signal absolutely explodes. On the flip side, if your weights are slightly below 1, like 0.5, multiply 10 times, the signal basically fades to 0. Exploding or vanishing, either way, your network is completely paralyzed. It just can't learn. So how do we fight this? Well, our first mechanics trick is normalizing our input data. We compute the mean, subtract it to center our data at 0, and divide by the variance to normalize the spread. Why go through the trouble? Because unnormalized data creates this stretched, wonky loss function that takes forever to navigate. Normalizing smooths our loss function into a nice, uniform, clean bowl. No matter where your algorithm starts on that bowl, the steepest slope points straight down to the minimum, making training incredibly fast and stable. Trick number 2 to fight off those villains is proper weight initialization, using clever math like the Glorot or Xavier methods. We can't just guess our starting weights, and we definitely can't make them all 0, or every neuron would learn the exact same thing. Instead, we use formulas that set the starting weights randomly, but crucially, they are proportional to the number of inputs feeding into them. It's usually something like 1 over the square root of the inputs. This brilliantly balances the network from the very first forward pass, preventing the signal from artificially swelling or shrinking as it moves through the layers. Which brings us to Section 5, Optimization, Training with Momentum. We are in the final stretch here. Now that our network is stable, how do we efficiently drive it through this massive mathematical landscape? We've got a choice to make. On one end, batch gradient descent processes your entire dataset before taking a single step. Sure, it's hyper-accurate, but if you have a dataset of 1 million images, it is painfully, unacceptably slow for a single update. On the other extreme, stochastic gradient descent updates the network after every single image. Lightning fast, yes, but it's incredibly noisy and chaotic, just ping-ponging all over the place instead of heading straight for the minimum. And this brilliantly illustrates why mini-batch gradient descent is the ultimate practical trade-off. Instead of 1 image or 1 million images, we process the data in manageable chunks, say 1,000 examples at a time. This keeps factorization fast on our hardware while still updating our network frequently enough to make rapid progress. But we can actually turbocharge this using momentum. Standard gradient descent just looks at where it is right now and takes a step. But momentum looks at its past updates and takes a moving average. Think of it like a heavy rocket trying to fly down a steep valley. If it only relied on the immediate slope, it would violently ping-pong off the walls of the valley. But because the rocket has physical momentum, its past forward speed smooths out those wild side-to-side swings, pulling it consistently and aggressively down the center of the valley to the absolute minimum. It's literally a single line of code that drastically speeds up training. We have covered some immense ground today, from the elegant calculus of the chain rule to the practical hackery of ReLU, normalization, and momentum. But I want to leave you with a final provocative thought. With all these optimized tools, our network can finally learn brilliantly. But how do we prevent it from becoming too good? How do we stop it from just rigidly memorizing the exact training data, instead of genuinely understanding the real underlying patterns? That introduces the fascinating world of regularization, which is exactly where our journey heads next time. Until then, keep analyzing, keep learning, and I'll catch you on the next explainer.